Good day, everyone. I am Jaey Trecia as Ellorimo, and I am pleased to discuss to you the lesson 2 of Module 8, which is the product and quotient theorems. So let me read to you the learning objectives. At the end of the lesson, students can first, find the product and write the result in rectangular form. Second, find the quotient and write the result in rectangular form. And then products of complex numbers and trigonometric function. Solve for the products of 1 plus I squared of 3 and negative 2 squared of 3 plus 2I. Note that I is an imaginary number. So using the FOIL method to multiply complex numbers in rectangular form, we find the product of the quantity of 1 plus I squared of 3 to the quantity of negative 2 squared of 3 plus 2I as follows. So 1 times negative 2 squared of 3 is equals to negative 2 squared of 3 plus 1 times 2I is equals to 2I plus I squared of 3 multiplied to negative 2 squared of 3, we have negative 2I to the quantity of 3, since square root of 3 multiplied to square root of 3 is square root of 9, and the square root of 9 is 3. Then I squared of 3 plus I squared of 3 multiplied to 2I, we have 2I squared square root of 3. Then we have negative 2 square root of 3 plus 2I minus 6I, since 2I multiplied to 3 is 6I, plus 2I squared square root of 3. We need to note that I squared is equals to negative 1. Then combine like terms, we have the product of negative 4 square root of 3 minus 4I. So solving for the product through converting the complex numbers to trigonometric form, given 1 plus I squared of 3 is equals to 2 to the quantity of cos 60 degree plus I sin 60 degree, and negative 2 square root of 3 plus 2I is equals to 4 to the quantity of cos 150 degree plus I sin 150 degree. Therefore, we have 2 to the quantity of cos 60 degree plus I sin 60 degree multiplied to 4 to the quantity of cos 150 degree plus I sin 150 degree is equals to 2 multiplied by 4 as an absolute value is equals to 8. Then cos 60 degree times cos 150 degree plus I sin 60 degree times cos 150 degree plus I cos 60 degree multiplied by sin 150 degree plus I squared sin 60 degree times sin 150 degree. Then we have 8 for 2 times 4 is equals to 8, and cos 60 degree times cos 150 degree minus sin 60 degree times sin 150 degree plus I to the quantity of sin 60 degree times cos 150 degree plus cos 60 degree minus sin 150 degree. For we have to factor out the I, and I squared is equals to negative 1, and we need to note that. Then therefore we have 8 cos to the quantity of 60 degree plus I plus 150 degree plus I sine to the quantity of 60 degree plus 150 degree. Then we have the product of 8 to the quantity of cos 210 degree plus I sine 210 degree. The absolute value of the product 8 is equal to the product of the absolute values of the factor 2 multiplied to 4. So the argument of the product 210 degree is equal to the sum of the arguments of the factors 60 degree plus 150 degree. The product obtained when multiplying by the first method is the rectangular form of the product obtained when multiplying by the second method. So 8 cos 210 degree plus I sin 210 degree is equals to 8 to the quantity of the trigonometric value of cos 210 degree is equals to negative square root of 3 over 2 plus I sin 210 degree. Note that sin 210 degree is equals to negative 1/2. Therefore, we have to subtract negative square root of 3 over 2 minus 1/2 I. Then we have the product, or rather the rectangular form as equals to negative 4 square root of 3 minus 4I. Then the product theorem. Multiplication of complex numbers in polar form is similar to the multiplication of complex numbers in standard form. However, to determine a general rule for multiplication, the trigonometric functions will be simplified by applying the sum difference identities for cosine and sine. To obtain a general rule for the multiplication of complex numbers in polar form, let the first number be r sub 1 to the quantity of cos theta sub 1 plus I sin theta sub 1. And the second number be r sub 2 to the quantity of cos theta sub 2 plus I sin theta sub 2. The product can then be simplified by use of three facts. First, the definition I squared is equals to negative 1. Second, the sum identity of cos alpha cos beta minus sin alpha sin beta is equals to cos quantity of alpha plus beta. And lastly, the sum identity sin alpha cos beta plus cos alpha sin beta is equal to sin quantity of alpha plus beta. Then, solution for the product of r sub 1 to the quantity of cos theta sub 1 plus I sin theta sub 1 multiplied to r sub 2 to the quantity of cos theta sub 2 plus I sin theta sub 2 is equals to r sub 1 multiplied to r sub 2 quantity of cos theta sub 1 multiplied to cos theta sub 2 plus I cos theta sub 1 multiplied to sin theta sub 2 plus I sin theta sub 1 multiplied to cos theta sub 2 plus I squared sin theta sub 1 sin theta sub 2. Then we have r sub 1, r sub 2, absolute bracket of the quantity of cos theta sub 1, cos theta sub 2 minus sin theta sub 1, sin theta sub 2, plus I to the quantity of sin theta sub 1 and cos theta sub 2 plus cos theta sub 1 multiplied to sin theta sub 2. And then we have the r sub 1, r sub 2 to the bracket of cos to the quantity of theta sub 1 plus theta sub 2 plus I sin to the quantity of theta sub 1 plus theta sub 2. Therefore, the product of r sub 1, quantity of cos theta sub 1 plus I sin theta sub 1 multiplied to r sub 2, the quantity of cos theta sub 2 plus I sin theta sub 2 is equals to r sub 1, r sub 2, close bracket of cos to the quantity of theta sub 1 plus theta sub 2 plus I sin to the quantity of theta sub 1 plus theta sub 2. So, and this is the product theorem. If r sub 1 of the quantity of cos theta sub 1 plus I sin theta sub 1 and r sub 2, the quantity of cos theta sub 2 plus I sin theta sub 2 are any two complex numbers, then the following holds r sub 1, r sub 2 with a closed bracket cos to the quantity of theta sub 1 plus theta sub 2 plus I sin to the quantity of theta sub 1 plus theta sub 2. In compact form, this is written as the quantity of r sub 1 cis theta sub 1 multiplied to the quantity of r sub 2 cis theta sub 2 is equals to r sub 1, r sub 2, cis to the quantity of theta sub 1 plus theta sub 2. So that is to multiply complex numbers in trigonometric form, multiply their absolute values, and add their arguments. So example 1 using the product theorem. So find the product of 3 quantity of cos 45 degree plus I sin 45 degree and 2 quantity of cos 135 degree plus I sin 135 degree. Write the answer in rectangular form. So the solution is 3 times 2 is equals to 6. So close bracket parenthesis of cos to the quantity of 45 degree plus 135 degree plus I sin 45 degree plus 135 degree. We have we have 6 to the quantity of cos 180 degree plus I sin 180 degree then equals to 6 cos the value of cos 180 degree in trigonometric is negative 1 and plus I, then the value of sin 180 degree is 0. Therefore, we have the product of negative 6. So quotients of complex numbers in trigonometric form. The rectangular form of the quotient of 1 plus I square root of 3 and negative 2 square root of 3 plus 2I is found as follows. So the solution is equals to 1 plus I square root of 3 divided by negative 2 square root of 3 plus 2I. Therefore, we need to multiply both numerator and denominator by the conjugate of the denominator. Then we have the quantity of 1 plus I squared of 3 to the quantity multiplied by the quantity of negative 2 squared of 3 plus 2I divided by the quantity of negative 2 squared of 3 plus 2I to the quantity of negative 2 squared of 3 plus 2I equals to negative 2 squared of 3 minus 2I minus 6I minus 2I squared of 3 divided by 12 minus 4I squared. Using the simplification, nakibali, then is equals to negative 8I over 16, then a lowest term is equals to negative 1 half I. So writing 1 plus I squared of 3, negative 2 squared of 3 plus 2I, and negative 1 half I in trigonometric form. So in finding the trigonometric form of those complex numbers, we use r is equals to the square root of x squared plus y squared. And finding the theta, we have tan theta is equals to y over x, or the opposite over adjacent. So 1 plus I squared of 3 is equals to 2 quantity of cos 60 degree plus I sin 60 degree. Then negative 2 squared of 3 plus 2I is equals to 4 quantity of cos 150 degree plus I sin 150 degree. And then lastly, the negative 1 half I is equals to 1 half close bracket parenthesis of cos negative 90 degree plus I sin negative 90 degree. So quotient theorem. Division of complex numbers in polar form is similar to the division of complex numbers in standard form. However, to determine a general rule for division, the denominator must be rationalized by multiplying the fraction by the complex conjugate of the denominator. In addition, the trigonometric function must be simplified by applying the sum difference identities for cosine and sine, as well as one of the Pythagorean identities. So to obtain a general rule for the division of complex numbers in polar form, let the first number be r sub 1, the quantity of cos theta sub 1 plus I sin theta sub 1, and the second number be r sub 2, and the quantity of cos theta sub 2 plus I sin theta sub 2. The product can then be simplified by use of 5 facts. So first, the definition I squared is equals to negative 1. Second, the difference identity of cos alpha multiplied to cos beta plus sin alpha sin beta is equals to cos the quantity of alpha minus beta. And the third is the difference identity sin alpha cos beta minus cos alpha sin beta is equals to sin to the quantity of alpha minus beta. And the Pythagorean identity, then lastly, the fact that the conjugate of cos theta sub 2 plus I sin theta sub 2 is cos theta sub 2 minus I sin theta sub 2. So here is how we find the general form when the general form of the quotient theorem. We have r sub 1 quantity of cos theta sub 1 plus I sin theta sub 1 divided by r sub 2 quantity of cos theta sub 2 plus I sin theta sub 2. We have r sub 1 quantity of cos theta sub 1 plus I sin theta sub 1 over r sub 2 quantity of cos theta sub 2 plus I sin theta sub 2. Then we need to multiply both numerator and denominator by the conjugate of the denominator. Therefore, we need to multiply cos theta sub 2 minus I sin theta sub 2 over cos theta sub 2 minus I sin theta sub 2 to the given factors. So therefore, we have r sub 1 over r sub 2 multiplied to cos theta sub 1 cos theta sub 2 minus I cos theta sub 1 sin theta sub 2 plus I sin theta sub 1 cos theta sub 2 minus I squared sin theta sub 1 sin theta sub 2 over cos squared theta sub 2 minus I squared sin squared theta sub 2. Then we have the r sub 1 over r sub 2 multiplied to the quantity of cos theta sub 1 cos theta sub 2 plus sin theta sub 1 sin theta sub 2 plus I in the quantity of sine theta sub 1 cos theta sub 2 minus cos theta sub 1 sine theta sub 2 over cos squared theta sub 2 plus sine squared theta sub 2. Therefore, we have r sub 1 over r sub 2 with the close bracket parenthesis of cos quantity of theta sub 1 minus theta sub 2 plus I sine quantity of theta sub 1 minus theta sub 2. So in general form, we have r sub 1 in the quantity of cos theta sub 1 plus I sine theta sub 1 divided by r sub 2, quantity of cos theta sub 2 plus I sine theta sub 2 is equals to the absolute values of r sub 1 over r sub 2 to the quantity of cos, to the close bracket parenthesis of cos quantity of theta sub 1 minus theta sub 2 plus I sine to the quantity of theta sub 1 minus theta sub 2. And this is the quotient theorem. And in compact form, this is written as r sub 1 cis theta sub 1 over r sub 2 cis theta sub 2 is equals to r sub 1 over r sub 2 cis to the quantity of theta sub 1 minus theta sub 2. That is, to divide complex numbers in trigonometric form, divide their absolute values, and subtract their arguments. Example. Using the quotient theorem, find the quotient of 10 cis negative 60 degree divided by 5 cis 150 degree. 10 and 5 are the absolute values. So we have 10 divided by 5 cis. Negative 60 degree minus 150 degree is equals to 10 divided by 5 is 2. Copy cis. Negative 60 degree minus 150 degree is equals to negative 210 degree. Therefore, we have 2 close bracket parenthesis of cos negative 210 degree plus I sine negative 210 degree. Then we have 2 close bracket parenthesis of negative square root of 3 over 2 since the trigonometric value of cos negative 210 is equals to negative square root of 3 over 2 plus I 1/2 since the value of sine negative 210 is 1/2. Therefore, the quotient of 10 cis negative 60 degree over 5 cis 150 degree is negative square root of 3 plus I. Here is another example of the quotient theorem. Find the quotient of the quantity of square root of 3 minus I divided by the quantity of 2 minus I 2 square root of 3. First, we need to express each number in polar form. So in finding the trigonometric form of those complex numbers, we use the formula of r is equals to the square root of x squared plus y squared. Then let the quantity of the square root of 3 minus I be r sub 1 and the quantity of 2 minus I 2 square root of 3 be the r sub 2. Then to compute the quantity of square root of 3 minus I, we have the square root of 3 as the x value and the I as the y value, or rather the negative 1 since I is negative 1. Then supply the given values. We have r sub 1 is equal to the quantity of square root of 3 squared plus negative 1 squared. Hence, square root of 3 squared is equal to square root of 9 and the square root of 9 is 3 plus negative 1 squared is 1. So 3 plus 1 is equal to the square root of 4 and the square root of 4 is equal to 2. Therefore, our r sub 1 is equals to 2. And then, the quantity of 2 minus I 2 square root of 3 is our r sub 2. In this quantity, our x value is 2 and our y value is 2 square root of 3. Then, supply those given values to the formula as r sub 2 is equals to square root of x squared plus y squared. We have the square root of 2 squared plus negative 2 square root of 3 squared. Then 2 times we have r sub 2 is equal to square root of 16 and the square root of 16 is equals to 4. Therefore, our r sub 1 is 2 and our r sub 2 is 4. Here we have to compute r sub 1 divided by r sub 2 is equals to 0.5. Since the square root of 16 divided by square root of 4 is 0.5, or either 4 over 2 is 0.5. Then next is we need to find the theta values of those quantities. Same quantities for theta. Theta sub 1 will be the square root of 3 minus I, and theta sub 2 will be 2 minus I to square root of 3. Hence the x values and y values are the same. We have we need to compute theta sub 1 is equals to tan. The inverse of tan, theta sub 1 is equals to the inverse of tan of the quantity of negative 1 over square root of 3 is equals to 5.75959 rad, and the theta sub 2 is equals to the inverse of tan negative 2 square root of 3 over 2. We have the given value as 5.23599 rad. So to find the value of theta in those quantities, we have theta minus theta sub 1 minus theta sub 2. Therefore, we have theta sub 1 as 5.75959 minus theta sub 2, 5.23599. We have the given theta of 0.5236. So now plug in what we found to the quotient theorem. So the theorem of the quotient theorem is r sub 1 over r sub 2 close bracket parenthesis of cos to the quantity of theta sub 1 minus theta sub 2 plus I sine the quantity of theta sub 1 minus theta sub 2. We have 0.5 quantity of cos 0.5236 plus I sine 0.5236, and that is the quotient theorem of those given quantities. And that ends of my presentation. Thank you and God bless all.